is 1 upon x. So for the reactance circle, we plotted here. This is the plot for the reactance circle. Why they are asking? Waiting in the lobby. Okay, so this is the case for the reactance circle. So what is the center? 1 comma 1 by x and radius is 1 upon x. Okay, so for this case, this is the plot for the reactance circle. See, reactance could be positive or negative, so x could be plus minus infinity also. So the value of x we have taken from 0 to plus minus infinity. If it is positive, then inductive reactance. If it is negative, then capacitive reactance. So 0 to plus minus infinity. So what will be the center then? Center is 1 comma. Center is at 1 comma 1 upon x. Radius is 1 upon x. Okay. So when the reactance is 0, what will be center and radius? 1 comma infinity. 1 comma infinity will be center. Radius will be infinity. So radius is infinity means a straight line. So when the normalized reactance x is equal to 0, so see here, this is the reactance circle, x is equal to 0. And center is 1 comma infinity. So basically it will be a line. And when the x is equal to plus 1 by 2, what will be radius? Radius will be 2 and center will be 1 comma 2. So center will be 1 comma 2, radius will be 2. So for x is equal to 1 by 2, the center is 1 comma 2 for this circle. Only part of the circle is shown here, which is inside this outermost circle. And what will be radius? Radius will be 2. Similarly, when x is equal to 1, what will be center and radius? Center is at 1 comma 1 and radius is at 1. So radius is 1, center is at 1 comma 1. Similarly, for x is equal to 5, it is shown here, x is equal to 2, x is equal to infinity. When x is equal to infinity, center will be 1 comma 0, radius will be 0. Point circle. So x is equal to plus minus infinity, center is at 1 comma 0. 1 comma 0 and radius is 0. So this is the normalized reactance circle. We have so now we have the Smith chart. Okay. So here is Smith chart. So what are the properties of the Smith chart? You are seeing the Smith chart here. This is the impedance Smith chart. Now a standing wave ratio circle. So a standing wave ratio S is equal to 1 plus mode of gamma divided by 1 minus mode of gamma. And gamma is equal to mode of gamma plus and angle of theta gamma. Reflection coefficient. Okay. So basically the standing wave ratio S is equal to 1. Where S is equal to 1, S is equal to 2. So here you are seeing 1.0. So it will be a point circle because S is equal to 1 means reflection coefficient is 0. Reflection coefficient is 0. So 0 comma 0 it is here. So S is equal to 1, it is a point circle. And S is equal to 2.0, this circle. So where it is crossing the positive gamma r axis, So positive gamma r axis, it is crossing at here, it is retained 1.4, 1.7 for 2.0. So basically, S is equal to 2.0 is this circle. Similarly, S is standing wave ratio is equal to 3. So if we have to plot this circle, on this circle S is always equal to 3. So we have to check the positive gamma r axis. So here it is written 3.0. So basically this circle will cross the positive gamma r axis at 3.0. So S is equal to 3. So this way you can plot the standing wave ratio circle also. And where is a PSC and POC located? Open circuit point and short circuit point. So for the short circuit point, what will be the load impedance? 0 plus J into 0. 0 plus ZL is equal to 0 plus J into 0. So ZL is equal to 0 plus J into 0. So where that will be located? Short circuit point. What will be the reflection coefficient? What will be the reflection coefficient? -1. The reflection coefficient will be equal to -1. That is here, short circuit point. And for the open circuit point, what will be ZL? Infinity plus J into infinity. So what will be the reflection coefficient? ZL minus Z0 divided by ZL plus Z0. That will be 1. It is here, open circuit point, POC. So on this Smith chart, you are seeing the resistance circles and the reactance circles. The positive reactance circles, the negative reactance circles, and the resistance circle. So where is R is equal to 1 circle? Where is R is equal to 1 circle? Can we locate that? R is equal to 1 circle on the Smith chart. So see here, R is equal to 1 circle is here. See, it is written R is equal to 1.0. This circle we are talking, R is equal to 1 circle. Where is R is equal to 2 circle? R is equal to 2 circle. It is here. R is equal to 1.0. So now some properties of the Smith chart we will see. So the short circuit point I told you. So the location of the short circuit point and the open circuit point. Okay. So now a complete revolution 360 degree around the Smith chart. It represents lambda by 2 of the transmission line. What that means? A complete revolution 360 degree on the Smith chart corresponds to lambda by 2 distance of the transmission line. What that means? Can you explain this by seeing the Smith chart? Can you explain? 360 degree revolution on the Smith chart corresponds to lambda by 2 distance on the transmission line. What is the meaning of that? See here. See this Smith chart. So from 0 to outermost scale I am talking. So from 0 to 0.25. You are seeing here. We are starting from 0, 0.01, 0.02, and so on in the outermost scale I am talking. So 0.025. So 0.25 lambda. 0 to 0.25 lambda. That means 180 degrees. Am I correct or not? I am only talking about the half of the chart. I am moving from here to here. So 0.25 lambda corresponds to 180 degree on the Smith chart as per this chart. Okay, so what will be 0.5 lambda? That will be corresponding to 360 degree. So lambda by 2 corresponds to 360 degree. So one complete revolution corresponds to lambda by 2 distance of the transmission line. Is it okay for you? So that means lambda corresponds to 720 degree. If lambda by 2 corresponds to 360 degree, so lambda corresponds to 720 degree. Here lambda corresponds to 720 degree. Yes. So a complete revolution represents the distance of lambda by 2 on the transmission line. Clockwise movement. Now see clockwise and counterclockwise movement. So clockwise movement on the Smith chart is regarded as moving toward the generator. Moving toward the generator. So see here, it is written here moving wavelength toward generator. Outermost circle wavelength toward generator and middle scale wavelength toward load. So wavelength toward generator. So clockwise movement means you are moving toward the generator. Counterclockwise movement on the Smith chart means you are moving toward the load. So moving toward the generator means what? Away from the load. If we are moving from the toward the generator, that means we are moving away from the load. We are moving away from the load. Okay. So next, clockwise movement means moving toward the generator as per the Smith chart. Okay. Counterclockwise movement means moving toward the load. Now see here, moving toward the load means counterclockwise. Counterclockwise. Moving toward the load. It is shown here in this figure, you can see clearly. Toward generator means clockwise. Towards load means counterclockwise. Okay. This is outermost scale, this is middle scale, this is innermost scale. Okay. So towards generator means we are moving clockwise. Clockwise means towards generator or away from the load, same thing. Or counterclockwise means we are moving towards the load. So towards the load means away from the generator. Same thing. Away from the generator or towards the load, same thing. That is counterclockwise. Now suppose we are at load and we make a counterclockwise movement. What that means? Can anybody tell? We are at the load and counterclockwise movement means what? When we are already at the load, so how we will move towards the load? When we are already at the load. So what that means? So when we are at the load, so moving towards the load does not mean anything. Okay? It does not make sense because we are already at the load. So similarly, when you are at the generator end and you make a clockwise movement, that does not make any sense because towards the generator you are already at the generator. So now let us talk about the three scales. We are seeing outermost scale, middle scale and protractor innermost scale. So what is the meaning of three types of scale? So any one scale you can use, but the meaning of the three types of a scale, outermost scale means it is used to determine the distance on the transmission line from the generator end. So outermost scale means it is used to determine the distance on the transmission line from the generator end, okay, in terms of wavelength. From the generator end in terms of wavelength. So outermost scale means we are measuring the distance from the generator end on the transmission line from the generator end. If we use the outermost scale on the Smith chart, this kind of setting is done. I have to again let in what is and why we are joining at 10:35. Okay, so outermost scale means we are measuring distance on the transmission line from the generator end. And middle scale means so that means distance from the load end. Distance from the we are measuring distance on the transmission line from the load end. If you use the middle scale. Innermost scale means it is a protractor in degrees and it will give you the angle of the reflection coefficient, simple, theta gamma, angle of the reflection coefficient. So that is the job of the innermost scale, angle of the reflection coefficient it will give you. You are seeing here 180 degree, 135 degree, theta gamma, angle of reflection coefficient. Okay, so now lambda by 2, you know, corresponds to 360 degree. Just I explained just now that lambda by 2 distance on the transmission line corresponds to 360 degree angle on the Smith chart. So that means one complete wavelength means 720 degree on the Smith chart. So lambda distance on the transmission line corresponds to 720 degree movement on the Smith chart. Okay. So now which scale we have to use? Protractor scale or from the generator end or from the load end, that we will see. But outermost scale means from the generator end we are measuring. Middle scale means from the load end we are measuring on the transmission line. And innermost scale means it is the angle of the reflection coefficient, theta gamma. Okay, other properties of Smith chart is, now the question is where is Vmax and Vmin? Where is Vmax and Vmin? Maximum voltage and minimum voltage on the transmission line, or maximum input impedance and minimum input impedance on the transmission line, which is terminated in a load impedance ZL. So we want to find what is the location of the maximum and minimum voltage and maximum and minimum input impedance. If you remember the theory, so what is the relationship between maximum and minimum voltage? See here, Z in max, magnitude of Z in max, input impedance maximum, is equal to Vmax upon Imin. So that means the location of maximum voltage will be where the input impedance will be maximum from this equation. Okay. And what about Vmin? So Z in mean is equal to V mean upon I max. So minimum voltage means where the input impedance is minimum. Now this theory you remember and come here. So where will be maximum and minimum voltage? So where will be minimum and maximum voltage? Where the input impedance. So we are here talking about the normalized impedance, that will be maximum. So that will be on the positive gamma R axis. Real part of reflection coefficient gamma R, positive gamma R axis. Okay. And where will be location of the minimum voltage? It will be located on the negative gamma R axis. See here it is written 0, 0.1, 0.2. We are talking about the normalized input impedance. And here it is 1 and 1.2, 2.0 up to infinity. From 0 to infinity. Input impedance. Okay, so maximum and minimum voltage location, did you get or not? On the Smith chart. So Z in max, mode of Z in max is equal to V max upon I min. So V max occurs where Z in max is located. That is on the positive gamma R axis. So positive gamma R axis means this is here OPOC. It is written as POC, point of open circuit, and it is O. So OPOC on this line. Location of the on this axis, OPOC axis. Okay. So location of the maximum voltage. What about the location of the minimum voltage? So location of the minimum voltage. So that is on the OPSC axis. OPSC axis. Okay. Okay, good. So voltage, maximum voltage and minimum voltage, and what will be the distance between the maximum and minimum voltage on the Smith chart? So that will be 180 degree apart on the Smith chart. On the transmission line it is lambda by 4. On the transmission line it is lambda by 4 distance. So distance between maxima and minima, lambda by 4. Maxima and minima, lambda by 4. And on the Smith chart, lambda by 4 corresponds to 180 degree, because lambda by 2 corresponds to full revolution. So 180 degree means lambda by 4 on the line. Okay. So next point is we can use the Smith chart both as impedance and admittance chart, because admittance is equal to Y is equal to reciprocal of impedance 1 upon Z. So for admittance chart can be, so circuit, this will correspond to R and S. Conductance and susceptance circle. Conductance and susceptance circle will correspond to resistance and reactance circle. So I will provide you one Smith chart having both the impedance and admittance chart. And there are applications of admittance chart also, particularly for designing the matching network, which will match the transmission line impedance with the load impedance. Okay, so next we will solve some question. This convention you must remember. Clockwise movement on the Smith chart means we are moving toward the generator on the transmission line. And when we are moving toward the load on the transmission line, that means we have to move counterclockwise in counterclockwise direction on the Smith chart. And 3 scales means outermost scale means we are measuring distance on the transmission line from the generator. Middle scale means from the load end, and innermost scale means it is a protractor, so it will give the angle of the reflection coefficient theta gamma. So towards the generator in movement, because here is generator, here it is load, transmission line terminated in load, so towards the load, is that thing I discussed. Okay, so now you will learn Smith chart while solving some numerical. Only theory will not serve any purpose. Theory is good, but numerical you have to do. So the first question is taught to you. You have to solve this question using both the analytical approach and Smith chart, graphical technique. Here is the question. A 30-meter long lossless transmission line. So length of the line is given. It is 30 meters and width Z0. So characteristic impedance of the transmission line is given. 50 ohm. Frequency is given. 2 megahertz. You can calculate the wavelength because F is given. So lambda you can calculate. Is terminated. Load impedance is given. So normalized load impedance first you calculate. ZL by Z0 and phase velocity is 0.60 on the line. You have to find these three things: reflection coefficient, standing wave, and input impedance. Okay. So first use the theoretical method. Then Smith chart. Okay. So solve this question. Reflection coefficient you have to calculate a standing wave ratio and input impedance. First calculate the wavelength. It is given and frequency is also given. Okay, solve this. So what is the reflection coefficient? ZL minus Z0 divided by ZL plus Z0. So how much you are getting? So what is the value? What is the value of the reflection coefficient? So reflection coefficient is equal to 0.3523. Magnitude, angle is 56 degree. So using this formula, direct formula, without Smith chart. A standing wave ratio. So 1 plus mode of gamma divided by 1 minus mode of gamma. So 1 plus, what was the magnitude? 0.3523. 1 plus 0.3523 divided by 1 minus 0.3523. What is the value? What is the value of the standing wave ratio? What is the value? What you are getting? A standing wave ratio. So it is equal to 2.088. Okay, and what is the beta L? Because for input impedance you have calculate beta into L. So beta is equal to Mayank. There is okay. So what is input impedance? So here is the formula 10 beta L. So input analytical using without impedance, without Smith chart, using that formula. Okay, now use Smith chart and solve reflection coefficient, standing wave ratio, and input impedance using Smith chart. Theoretically, we have seen how to solve this using Smith chart. So first, you calculate the normalized load impedance. That will be basically 60 plus j into 40, 60 plus j 40 divided by 50. 1.2 plus j into 0.8. Resistance circle R is equal to 1.2. Reactance circle X is equal to 0.8. Locate the load. Where is the load on the Smith chart? Locate the load point. So intersection of two circles. Resistance circle 1.2 and reactance circle 0.8. Locate on the Smith chart. So 1.2, where is 1.2? 1.2 resistance circle is here. X is equal to 0.8, where 0.8 is here. So intersection of this circle and 0.8. So here is your load, ZL. This is your load. So now question is how to calculate the reflection coefficient. So how to calculate load point we have done. So what will be the reflection coefficient? Magnitude and angle, both. So you know this is a unity radius, the outermost circle. So basically, what is the distance OP? Because all the impedances are normalized. So what will be OP divided by OQ? So using a straight edge, you can calculate OP and you can calculate OQ also. So the magnitude of reflection coefficient at the load will be equal to OP by OQ. OP by OQ. So what will be OP by OQ? That you can measure using a scale. So 3.2 centimeter by 9.1 centimeter. You can measure this distance. So this is 3.2 centimeter and here it is 9.1 centimeter OQ. So what will be the magnitude of the reflection coefficient? 0.3516 using Smith chart. And using formula, what we were getting? 3523, which is more accurate? Using direct formula or using Smith chart? Which is more accurate? The more accurate is using the formula. Smith chart result will be, it is okay, it will serve the purpose, but it is less accurate than the using the direct formula. Okay. So mode of gamma is 0.3516, but it is easier to calculate without using any formula. You can calculate just by measuring locating the load impedance point T and measuring OP and OQ. So okay, now the question is how to calculate the angle of the reflection coefficient. We need both magnitude and angle. So what will be angle? Angle of the reflection coefficient. The innermost scale will give you the angle of the reflection coefficient. What you are saying here? This is 40 degree, 50 degree, 60 degree, 70 degree. So it is between 50 and 60 degree. And if you see closely, it is between 55 and 60. So 56 degree. 56 degree is the angle. As per the Smith chart. Theoretically, using formula, it is also 56 degree. Okay, good. So both are giving the same result for the angle. So what was the part B of the question? A standing wave ratio. A standing wave ratio. How to calculate the standing wave ratio for this problem? Yes, what will be a standing wave ratio? We have to plot a circle using this point, load point, center is here. Okay, here is the circle. Question is, what is a standing wave ratio? Where this circle is crossing the positive gamma axis, it is crossing the positive gamma axis at somewhere 2.0 and 2.2. So it is, I think, 2.05. What do you say? So 2.1 they have taken. No problem. Okay, what was the result using theory? 2.088. So my guess is more correct. 2.05. Exactly it is 2.088 as per the theory. As per Smith chart, I am seeing here it is more close to 2.05, 2.08. So if you take 2.1 also, full marks will be given. Because Smith chart will not give you the exact result. Okay, it will give you the approximate result, the close result, close to the exact. Okay, what is the next question? 2.088, it is done. Reflection coefficient is done. The input impedance. How to calculate the input impedance? How to calculate? Length of the transmission line is given in this question. What is the length of the line? It is given 30 meter long. 30 meter long. Okay, what is lambda? Wavelength. Can you tell what is wavelength? Length is 30 meter. It is given. So I want to calculate 30 meter is corresponding to what wavelength? Wavelength is, I am asking you what is wavelength. Wavelength is lambda is equal to 2 pi by beta. Beta is omega upon velocity. So omega upon velocity. Omega is 2 pi f. 2 pi into 2 into 10 to the power 6. Divide by 0.6 into 3 into 10 to the power 8. So basically lambda will be 2 pi upon beta. So lambda will be basically u upon f directly. So u upon f means 0.6 into 3 into 10 to the power 8 divided by 2 into 10 to the power 6. So that will be equal to 0.6 into 3, 1.8 divided by 2. So 0.9 into 10 to the power 2. So 90 meter. 90 meter is the wavelength. Lambda is 90 meter. And length of the institution length of the line is 30 meter. Okay. So that means we can say that length is 1 by 3 into lambda. Is there any problem? Lambda is 90 meter, length is 30 meter. So L is equal to lambda by 3. L is equal to lambda y 3, 1/3 of the wavelength. So how much we have to move on the Smith chart? from the load we have to move. We have to move from the load. So from the load means counterclockwise direction. Counterclockwise direction. How much we have to move? Lambda by 3 distance. Lambda by 3 means how much angle? Lambda means 720 degree. Lambda by 3 means 240 degree. 240 degrees we have to move in the counterclockwise direction. Then we will get normalized input impedance 240 degree. See here, 30 meter means 240 degree. So 240 degree we have to move. In which direction? In which direction? Oh, toward the generator. We have to move toward the generator. Toward the generator means it was clockwise. Toward the generator means clockwise, not counterclockwise. Counterclockwise means toward the load. We are moving toward the generator, Z in. So clockwise 240 degree. Clockwise 240 degree in clockwise direction. So clockwise direction 240 degree means counterclockwise 360 minus 240. Okay, no problem. Do not be confused. Move clockwise 240 degree from point this P point, load point. From load point, move 240 degree in the clockwise. That is clear. So towards the generator clockwise from the load. So 240 degree angle. So using a protractor, if we move from this point to 240 degree angle, we are here at this point, G point. So this is the input impedance. This is the input impedance. And so what is the value of this input impedance if you have to locate? So can you say what is the value of G? The intersection of the resistance and reactance circle. So what is the resistance and reactance here? What is the resistance and reactance? So 1.0, 0.8, 0.7, 0.6, 0.5, 0. So it is close to 0.5. 0.5. R is equal to 0.5, but 0.5 to 0.4. So 0.48 we can take. 0.48 R is equal to. What about X? X is equal to 0, 0.01, 0.02 and 0.03. So 0.48 plus J 0.03. See, that was my guess. I told 0.48 and 0.03. But your guess could be different. You can guess 0.47 plus J 0.035. There is nothing to guess. Basically, it will be intersection. You have to see what is R and X. Okay. When you will do it actually on the Smith chart, so then you can tell closely. So basically, R is equal to 0.47 and J 0.035. Okay. Using theory, what is the answer? What is the exact answer? Using theory, what is the answer? It is 23.97 plus J 1.35. What we had calculated is normalized. Now multiply by Z naught 23.5 plus J into 1.75. So see here, J 1.75, but exactly it is 1.35. 23.97 is exact. I told you image chart will not give you the exact thing, but it will give you close to the exact result. Okay, so which will serve the practical purpose for finding impedance or any reflection coefficient, standing wave ratio, input impedance, whatever. Okay, So first question we solved using the Smith chart technique and direct formula. Now second question is here in front of you. Solve this question. This question you solve. You have to calculate reflection coefficient, okay, load impedance also, input impedance. What is given? 70 ohm lossless line. A standing wave ratio is given. A standing wave circle you can plot first. S is equal to 1.6. Plot the standing wave circle. Angle of gamma is given. So you can calculate ZL. No problem. ZL you can calculate. And 0.6 lambda is also given. Length of the line is directly given in terms of wavelength. 0.6 lambda. So 0.6 into 720 degree. How much? So that angle you can calculate. From the load towards the generator we have to move. So we will move in clockwise direction towards the generator in clockwise direction. How much angle? Angle will be 0.6 into 720. So there we can locate input impedance. The distance of the first minimum voltage. So this type of question we have not done. So how to locate the first minima? The location of the minimum input impedance, that will give the first minima. So and it will be on the OP axis. So we can solve some question involving minima and maxima. The location of Vmax and Vmin with respect to the load. So this question. Okay, now solve this question. Load is given 100 plus J 150. So what will be normalized load impedance? 100 plus J 50, 150 divided by 75. So it will be 4 by 3 plus J3, J2, 150 by 75. So locate the normalized load impedance. Then easily you can calculate reflection coefficient, you know how. A standing wave ratio is also easy. Now the question is load admittance. This is interesting. How to calculate 1 upon ZL. So how to calculate 1 upon ZL? How to calculate? Property of lambda y for matching network you know or not? What was the formula? Zn is equal to Z naught square upon Zn. So Zin upon Z naught is equal to 1 upon normalized Zn. Normalized Zn will be Y. So YL, normalized YL will be equal to normalized input impedance if we use lambda y4. Okay, so see, first part is reflection coefficient. Now come on Smith chart. Locate load impedance first. Where is the load impedance? Reactance circle, X is equal to 2, R is equal to 4 by 3, 1.333. So where is R and X? X is equal to 2, this circle, and R is equal to 4y3. So R is equal to 4y 1.33. 1.33 is where, 1.2 is here, 1.4 is here, 1.3 somewhere here. This circle. So this is the location of the load point. X is equal to 2, 2.0, and R is equal to 1.3. Here is the location of the point. Okay, so now how to calculate the reflection coefficient? OP upon OQ, magnitude is done. Angle, directly you see from the inner scale. What is the angle? 30 degree, 40 degree, 50, so it is basically 40 degree. So both methods is done here. 40 degree, okay? 0.659 40 degree. So next we have a standing wave ratio. How to do? So plot a circle which goes through this load point, and where this circle is crossing the positive gamma R axis, that is a standing wave ratio. So 3.0, 4.0, 5.0. So from the Smith chart 4.82, and the exact value is 4.865. 4.865. So it is 3.0, 4.0. It is here 5.0. So close to 4.8 is taken. Okay. And what about the load admittance? We have to locate. How to locate that? From PO to PO P dash, constant S circle with PO P dash. A standing wave ratio. We have this point OP. OP. So P means load impedance. We have to calculate load admittance on this impedance Smith chart, where that impedance is located. Load admittance. So the method is, you can extend this line OP in the reverse direction, and where it is crossing the standing wave ratio circle, it is crossing here, P dash. So this point is the location of the load admittance. Now question is, what is this point? So this point R and X, you can see here what is resistance and reactance. So what is resistance for this point? 0.22. Can I take 0.2? And what is reactance? X is equal to minus, X is equal to minus 0.34 can be 0.34. Okay, so what is the admittance? Normalized admittance. Yes, minus 0.34 I had taken. It is minus 0.35. No issue. Minus 0.35, minus 0.34. Both are correct because it will not give you the exact result. Approximation. And this is, I had taken 0.22. It is 0.228 or 0.23, no problem. So now it is normalized. So the YL will be, okay, why not multiply with 1 upon 75? Okay. And what is the exact result? Exact is here. So it is close to exact, no problem. So next we have to do Zin at 0.4 lambda from the load. Good. So how to calculate the input impedance at 0.4 lambda from the load. So from the load means what? Towards the generator. From the load means towards the generator. Means clockwise direction we have to move. How much we have to move? In clockwise from the load, how much we have to move? 0.4 into 720 degree. So 0.4 into 720 means what? 288 degree. So 288 degree we have to move from the load point in the clockwise direction. That will give you the input impedance on the Smith chart. This is your load point. Now from here you have to move how much? 288 degree. So when you move 288 degree from this load point in the clockwise direction, you will reach here. What is this value? R and X for this point. So R will be basically 0.3 and it is 0.2. Okay, so 0.28 can be checked. And what is reactance for this point R? Reactance is between 0.6 and 0.65. Close to 0.65, 0.635 you can take. 0.635, not 0.6. So see now what is the answer. Yes, 0.63 is taken. Okay. 0.635 I had told, 0.63 is taken, and 0.3 is taken. 0.3. So this is basically 0.3, and I had taken 0.32. Okay, no problem. So okay, so now Zn is equal to this. What is the exact answer? Zn is, what is exact? It is 21.9 plus J 47.6. So what is the next question? Zn at 0.4 lambda is done. The locations of the Vmax and Vmin with respect to the load. If the line is 0.6 lambda long, so the length of the transmission line is given. It is 0.6 lambda. 0.6 lambda corresponds to how much angle on the line? So what will be the location of Vmax? The location of Z in max. V means the location of Z in mean. The location of Z in max will be at OP-OC axis. So OP-OC. Vmax at this axis. But the question is where? So for calculating the location of 0.6 lambda corresponds to how much? 1 revolution plus 432 degree. 432 degree. That means 360 degree plus 72 degree. So we will start from load and we will move towards the generator 432 degree. Yes. 1 revolution plus 72 degree. 1 revolution plus 72 degree. And reach at the generator clockwise direction at point G. Where is point G? 432 degree. From the load it is 1 revolution plus 72 degree in the clockwise direction. Okay, in the clockwise direction. We are here. at this point D. So now what will be the standing wave ratio? So what will be a standing wave ratio? So how this Vmax is calculated? We are at point G, and 360 we have passed because 360 plus 72. So corresponding to, we have passed through point T once and point S twice. Point T, where is point T? Here. One V minima and point S twice. Because for one clock by each, and again we are here at point G. So two times at point S and one time at point T. So it is Vmax here, and here it is Vmin. So that means Zin max and Zin min. So basically, what will be the maximum voltage? The location of the maximum voltage. So maximum voltage, we have two maxima. So first maxima 40 degree upon 720 degree by lambda. So from where we got 40 degree? From where we have got 40 degree? So Vmax and Vmin we will do. We will calculate tomorrow. Okay. Vmax and Vmin, and one more question is there. What is that? Zin at the generator. That you can easily do. Input impedance at the generator. So you have to move 0.6 lambda length of the line from the away from the load end towards the generator clockwise. That you can do easily. Location of Vmax and Vmin, tomorrow we will discuss. So if you have any question, you can ask me. Now I will stop the recording.
Can you share the slides?
The video recording I will share, and this material is from StudyCo.